Hey guys, we're going to talk about section 11.4 today, which is about series and the notations that we use for series. So the idea of a series is very closely tied to a sequence. In fact, it is just the sum of the terms of a sequence. So, for example, if we have this sequence 3 plus 7, 3, 7, 11, 15, and 19, the series that's defined by that sequence is 3 plus 7 plus 11 plus 15 plus 19, etc. So notice that this one is in fact an arithmetic sequence, and so this is going to be called an arithmetic series. Now we have something called partial sums. In in a couple branches of mathematics, calculus, analysis, etc., series are usually only dealt with when they're infinite. In those higher branches of mathematics, there's just not a lot of reason to talk about finite series. So this term partial sum comes from the fact that at some level, all series are assumed to be infinite, but then we just chop them off at a certain point. So the nth partial sum goes from 1 to n because we've chopped off whatever may be after that. So we'll use this S sub n notation to represent a partial sum. Okay, the n will tell you how many terms there are in that series. Another thing to be familiar with is summation notation. This is the capital letter sigma that you may have seen before. And then these pieces here, we have the k to begin with on the lower left, the index of summation. That basically tells you what variable shows up in the explicit formula in the top right explanation. It says explicit formula for the kth term. So the k in the bottom left tells you what the variable is in the formula that's to the right of sigma. Okay, and then the lower limit of summation you'll see is the 1. It doesn't always have to be 1. You can start at 0, you can start at 3, you can start at 10. The most typical starting point is 1. But whatever that number is, that's the number you're going to start with by, when you're plugging numbers into k. And then at the top, we have the upper limit of summation. That'll be the last number that you plug in for k. So for small sums, okay, like for this one here, this is the sum of 2k from 1 to 5. By the way, that's how we read these. We would read this as the sum of 2k from k equals 1 to 5. So in this relatively simple series, we evaluate just by plugging in 1, 2, 3, 4, 5. 1's the first number you plug in, 5's the last number you plug in, and when you add all those up, you get 30 for this particular summation. All right, here's a second example for us to look at. This is the sum of k squared from k equals 3 to k equals 7. So if you would like to do this one on your own first, go ahead and pause now and work it out, and then I will work it out for you here on the screen. So we start with 3, we go to 7, and we're just plugging it into the k squared. So we get 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and adding all of those together, we get 135. So geometric series can increase pretty fast depending on just what they are. Sorry, this is not a geometric series, so I don't know why I said that. Series in general can grow pretty fast. Let me just leave it at that. All right, arithmetic series. We talked in section 11.2 about arithmetic sequences. And an arithmetic sequence is one that either goes up or goes down by a fixed amount each time. Well, if instead of just dealing with a sequence, we're dealing with the sum of the terms in a sequence, then we have an arithmetic series. Okay, so you'll know them the same way that you knew an arithmetic sequence. We're either adding or subtracting the same amount each time as we go through the sequence. So we have a formula for finding the sum of an arithmetic series. And it's a fairly easy to use formula. N is the number of terms in the sequence. A sub 1 is the first term. A sub n is the last term, the nth term. And then we take all that and divided by 2. So as an example, let's say we have 5 plus 8 plus 11 plus 14, yada yada, up to 32. And we can first verify, we should first verify that this is actually arithmetic. And just kind of quickly scanning through all these terms, you can see that we're adding 3 each time, right? 5 plus 3 is 8, 8 plus 3 is 11, etc. So it is definitely arithmetic. You need to check that first. And then now that we have confirmed that, we need to know how many terms we have. Okay, so counting those up, it looks like we have 10 terms. We need the first term, and we need the last term. And if you put all those together, there's our first term, 10th term. Putting all those together, we get 10 times 8 plus 32. 8 plus 32 is 40. 40 times 10 is 400. And 400 divided by 2 gives us 200. So the sum of these of this arithmetic series is 200. All right, in 11.3 we talked about geometric sequences. We said that geometric sequences either increase or decrease by a fixed ratio for each successive term. And so, again, if instead of just dealing with a sequence, we're actually dealing with the sum of the terms in a sequence, then we call it a geometric series. So the formula for the geometric series is a little more complicated than it was for the arithmetic, but hopefully still fairly easy to understand. A sub 1 is the first term of the series. R is that common ratio that we talked about from 11.3. And n is the number of terms in the series. So as an example, we can look at this. One thing to note, if your r is a decimal value or a fraction, don't expect your answers to come out very pretty. This one is an example of one that does not, it doesn't have a very satisfying answer. It's a bunch of decimals, and just be prepared for that. It's fine. So here we have a sum, and one of the things that's important to point out is we know that this is a geometric series because k is in the exponent here. Okay, that's kind of the hallmark of identifying a geometric series or a geometric sequence. When you look at the formula, remember that the formula for the nth term of a geometric sequence was a1 times r to the n minus 1. So that exponent is what clues us in that we're dealing with a geometric series or a geometric sequence. So because we see this k in the exponent, we know that this is geometric. So there's a few things that we need to identify. We need to figure out what's a1 and what's r. So a1 we get just by plugging 1 into k. And 4 times 0.3 gives us 1.2, so that's our a1. And then whatever the exponent k is on, whatever the base of that exponent is, that's r. Okay, so in this case, the k is on 0.3, so r is 0.3. Now we plug those things into the formula. Okay, we've got 12 terms here, so this is S12. Take our first term, 1.2, times 1 minus 0.3 to the 12th, divided by 1 minus 0.3. And the only thing that I would really caution you on as you're doing these is to be careful in the calculator with parentheses. I didn't draw parentheses in the denominator of this fraction, but when you put them in your calculator, you really need them. Okay, so it may have been smart of me to put parentheses around that, not because they're necessary with the way I've written it, but because it's necessary in the calculator. So just be careful with that. What you should get is this 1.71428480.3, yada yada yada. This is, I think, a rational answer. It's a rational number, but I don't know how many decimal places it takes for it to terminate or to repeat. It's longer than my calculator can handle. So that's the answer for the finite geometric series. And you may have noticed the word finite up there in the top, and that's going to beg the question, well, could we have an infinite geometric series? And indeed, in some cases, we can. If r is between -1 and 1, okay, or another way of saying that is if the absolute value of r is less than 1, then we say that the series converges. okay, because the geometric sequence, the terms of the geometric sequence are getting closer and closer to 0 as n gets larger and larger. So, say your r was 1/2, okay, and your first term was 8. Okay, so you got 8, and then the next term would be 4, and the next term would be 2. You just keep dividing by 2 each time, right? So then 2, 1, 1/2, 1/4, 1/8, 1/16. We're getting smaller and smaller and smaller fractions as we go along. So the terms of the sequence are getting closer to 0, and so basically what ends up happening is once we get out far enough, we're essentially adding 0. As we add an infinite number of terms, those terms just kind of turn into zeros, sort of. So in a convergent series, we can use this much simplified formula here. You see the sigma with the infinity on top. The formula for finding that sum is just a sub 1 divided by 1 minus r. So, by the way, if we can't find the sum because the terms don't go to 0, we say that the series diverges as opposed to converges. Looks like I gave away part of the answer to my example before I showed you the example. The example question is 248.6 plus 99.44 plus 39.776, etc. First thing we want to figure out is this geometric? And so to do that, we would just take like 99.44 divided by 248.6, see what we get. Do the same thing with 39.776 divided by 99.44. Take any two successive terms, and divide them. So when we do that, we get 0.4. All right. So since our A1 term is 248.6, we just do that divided by 1 minus 0.4, and it gives us 414.3 repeating. So this formula for infinite geometric series is actually a little bit easier to use, even though the concept of an infinite series is a little harder to get our brains around. So we have, at this point, notice that we have 3 important formulas. Okay, we have one for arithmetic, we have one for finite geometric series, and we have one for infinite geometric series. So those 3 formulas are pretty significant, pretty important. You want to keep those kind of in your back pocket as you go forward. All right, so here we have an application problem where we are using what's called an annuity, okay, where we're putting money in on a regular basis, and we're also earning interest on the money that we're putting in, okay? So this is a little bit of a complicated thing to figure out without this idea of a geometric series. Each month we put in money, and each month we earn interest on that money. And then the next month we put in more money, and we earn a little more interest. And then the next month, more money, more interest, and so on and so forth. It's pretty complicated, and it gets it gets hard to do by hand pretty quickly. But if we recognize that what we're dealing with is a geometric series, then it makes it that much easier. So first thing we need to do is identify some things, such as how much, what's our starting amount? What's our first term? And our first term here would be 100. At the beginning of the first month, we put in $100. Now, our n, the number of terms we're going to have, we have to think about kind of carefully. We're going to do 10 years, and we're going to pay every month. So that's 120 months. So our n will be 120. And then finally, and this is probably the trickiest part, is we have to figure out r. Okay, not interest rate necessarily, but r for the geometric series. And it actually, r does stand for interest rate here, that's fine, but it's not an annual interest rate that we need because we're breaking things down into months. So what we've got to figure out is, if 9% is our annual interest rate, what's our monthly interest rate? So the best way to do that is to take 0.09 divided by 12 and add 1, okay? Because we are going to have a little bit more at the end of the month than we had at the beginning, right? So I want to take the money that I have and multiply it by 1.0075 so that I'll have, like in the first month, I'll have $100.75. Okay, I want the balance to go up, right? If I just did 0.0075, it's like my $100 is gone and all I have is 75 cents, which would not be good. So 1 plus the 0.09 divided by 12 gives us the r that we need. And now we just plug this into our finite geometric series formula. Okay, this one's finite because we're only doing it 120 times. We're not doing it an infinite number of times. So plugging all these pieces in and going to the calculator to evaluate these really, really large exponents, we get approximately $19,351.43. So the reason this is tricky is because of all of those 120 different scenarios. We're earning interest on 120 different amounts. First month it's $100. Second month it's $100.75, and then after that it just starts getting more and more complicated with more decimal places and whatever. So if you recognize that this is a geometric series, then it makes it a whole lot easier. One other thing to point out, at 9% interest, you earn a pretty significant amount of interest in 10 years. If they just had the $100 for 120 months, that would be $12,000 in this account. So we can see that they earn $7,351 above, in interest above what they put in. So there you go. There's probably the most common application problem for geometric series, and that wraps us up. Your homework is page 979, 7 through 25 odd, and 47. 47 is an annuity problem. The rest of them are just practicing working on arithmetic, geometric series, and summation notation. So let me know if you have any questions about this, and I will see you next time.